First, I'm going to change the names of some of the variables to help us keep track of what's going on here. This velocity is actually the rotational velocity of the first servo. Now that we have several different velocities, including end-effector velocities in X and Y, and velocities of both of the servos, I want to be more explicit here. So I'm going to change this to say theta 1 dot. This is the velocity of theta 1. I'll change it here also. And change it up here. Now, I want to control the velocity of servo 2 also, so I don't want to call this just increment. I'll need to keep track of which increment it is. So this is the increment for theta 1. Next, I want to control the velocity of the second servo also. I'm going to copy all three of these variables and then paste them, and then I'll change their names to have 2 instead of 1. Now, I can't change this angle 1 and angle 2 to theta 1 and theta 2, even though that is what these mean, because I've already used theta 1 and theta 2 for the names of the functions up here. So you'll just have to remember that the variables angle 1 and angle 2 are the variables theta 1 and theta 2. Now I'll copy both of these lines, paste them, and change the numbers to 2. Right now, this is set up to set a constant velocity. But I don't want a constant velocity. I'm going to need to change theta 1 dot and theta 2 dot as the manipulator moves in order to get a particular X and Y end-effector velocity. So in order to get theta 1 dot and theta 2 dot to change over time, I'm going to need to cut these lines and put them inside of this loop so that they can change as the motion happens. Now I'll need to copy this line and paste it so that we control the velocity of servo 2 also. And this line also. Okay, right now we're controlling the velocities of both of the servos. We would like to calculate the velocities of the servos based upon a target x dot y dot value to control the velocity of the end effector. For this, we're going to use the equations that we found in the last video. I'm going to start at the end of our equations and work my way back up. So we'll start with these equations that define theta dot based upon x dot, y dot, and the inverse Jacobian. I need to do these calculations inside the loop also because the values of the Jacobian matrix are going to change. So instead of setting theta 1 dot to a constant, I'm going to set theta 1 dot equal to J11, and then I'll do INV for the inverse, times X dot plus J12 INV for the inverse times Y dot. I'll make the same change down here. J21 inverse times X dot plus J22 inverse times Y dot. Now we have some errors here because we haven't defined the inverse Jacobian or the X dot and Y dot values. Let's go do X dot and Y dot first because they're easier. Up here, let's create a float called X dot. And for now, I'm just going to set X dot equal to 1. The units here will be something like centimeters per second, but we'll go back and fix our units later on. We'll do the same for Y dot. Now, back down here, we need to start to declare our inverse Jacobian. To find the parts of our inverse Jacobian, we'll use this matrix here. Notice that we have a multiplier out front, and then we have the parts of the Jacobian on the inside. Let's do this multiplier. I'm just going to call it multiplier. It's equal to 1.0 divided by J11 times J22 minus J12 times J21. Let's go declare some of these variables. We have float multiplier, and then we have all the parts of the inverse Jacobian, and then we have all the parts of the regular Jacobian. All right, let's go back down. Let's use this multiplier to get the parts of the inverse Jacobian. J11 inverse is equal to the multiplier times J22. J21 inverse is equal to the multiplier times negative J21. J12 inverse is equal to multiplier times negative J12, and J22 inverse is equal to the multiplier times J11. All right, as we're working our way back up, the next thing we need to do is say what each of these parts of the Jacobian matrix are equal to. So I'm going to try and type these in correctly, and then we'll test it and we'll find our errors as we go. All right, we still need to declare and set values for our link lengths. Back up at the top, we'll do float A2. Here you want to set the values that you have for your actual manipulator. For me, this value is about 5.0. And A4 for me is somewhere between 6 and 7. I'll do 6.5. Now I still get some warnings on my sines and cosines. Let's make sure we're set up to do mathematical functions. Up at the top, we'll do pound include math.h. Then we'll go to project, build settings. And we want to check the assembler. And in additional include directories, I'll type M and hit enter. And then I'll do the same in the compiler. M, enter. And in the linker, I'll do it 2 places here. I'll click OK, and now we're not quite done with our code, but I'm going to pause here and try to build it because I want to look for errors. Okay, if you have any errors here, stop and solve your errors before moving on. And once you've cleared up your errors, we'll take the next step. There are 2 more things we have to do before we test this. First, we have to give a start and stop condition to this operation. And secondly, we have to get our units right in all of these calculations. Let's begin with the start and stop conditions. First, take this line, which is setting the initial angle for the first servo, cut it, and put it up here. Then we'll change this 0, 0 to say angle 1. And now we'll do the same thing for the second servo. We'll do angle 2 equals something else. Let's set angle 2 equal to 90. And then change this to angle 2. Next, we need to fill in here some kind of a stop condition. Let's make the manipulator stop whenever it calculates an angle that is outside of its range. Both angle 1 and angle 2 can go between 0 and 180 degrees. So we'll say here, while angle 1 is less than 180 and angle 1 is greater than 0.0, and let's make this greater than or equal to for both of these things here, less than or equal to. And angle 2 is less than or equal to 180, and angle 2 is greater than or equal to 0.0. Next, we need to get our units right. Right now, angle 1 and angle 2 are in units of degrees, but when we do these calculations, we need them to be in units of radians. So let's convert to radians here. Then we calculate the Jacobian, calculate the multiplier, calculate the inverse Jacobian, calculate theta 1 dot and theta 2 dot, calculate the increment. Then the next thing we want to do is use the increment. So let's take these two lines and then before we set the angles, we'll convert back to degrees. Okay, now let's test this. Program the PSoC and watch the path that the end effector takes. Can you see why it takes the path that it does? Think back to what we set x dot and y dot to be. X dot is 1 and y dot is 1. So what angle would you expect the line path of the end effector to follow? If you have this correct, the end effector should move at a 45-degree angle between the x0 and y0 axes. Now, we've only put in a stop condition that prevents the two servos from moving outside of their ranges. We're still allowing the end effector to try to move outside the workspace. So you might find that the motion lasts too long and the end effector tries to move outside of the workspace. If you get this motion also, try this. Can you get the end effector to move in a straight line along the x-axis or on a straight line along the y-axis? Do this by changing the x dot and y dot values and using what we learned about path planning in the previous video. Secondly, can you figure out a way to stop the motion before the end effector leaves the workspace? In your lab submission for today, show me how you get the end effector to move in a straight line parallel to the x-axis and in a straight line parallel to the y-axis.